right? I mean, we got choices, right? Here's two schools of thought. One school of thought, you go, hey, hold on a second, that's just the differential of 1/2 x squared plus 1/2 y squared, right? So therefore the solution is 1/2 x squared plus 1/2 y squared equals to 1/2 r squared. I mean, obviously you should write the constant as 1/2 r squared, right? Clearly. So the solution is x squared plus y squared equals to r squared. That's a little bit of name your constants as it suits your purposes physics humor for you. I always had this question in physics, like we would be integrating something and we'd be like, 3c to the 2/3 power divided by 7. Like, why is the constant that? And then, of course, you would multiply by 3/2 and take the 7th power and your answer has a c in it. It's like, I think physics professors enjoying doing this just to mess with students, because the student who's really lost, it makes it so much worse. Unnecessarily so. You could have just called the stupid thing C, and whatever. Anyway, so I did that to you here, although in a less malevolent fashion. And so, of course, the solutions are circles, right? The other way we could solve this, Calc 2 style, would be what? This is y dy equals minus x dx. You integrate both sides. You get 1/2 y squared is equal to minus 1/2 x squared plus some constant back there, right? So what's the nature of the solution set to this differential equation? What's it look like? What's that?
You just said it,
right? Oh, yeah. Sorry. You're right. Like, right. For each choice of R, we get a different circle, right? In fact, so basically there's a system of coordinates, right, where the choice of the one coordinate just tells you which solution you're on. In particular, you can use x is equal to r cosine theta, right? Y is equal to r sine theta. So in those polar coordinates, the solution just becomes what? R is equal to r, right? And then the theta just kind of goes around. But there's more than that I'd like to point out from this example. It's kind of a nice feature here. If you take any point in the plane, right? Take any point in the plane, say this one, how many solutions, well, there's a unique solution that goes through that point, right? You tell me the, tell me the theta, you tell me the r. Well, it's just on that one circle, right? And those circles fill the plane, right? This is an example of what's known as a foliation. All right, a foliation. So this is, there's a more general idea. You can basically, here's the general idea of a foliation. What is it? The manifold is parsed into leaves, right? These leaves fill the entire space, the entire manifold M, all right? And it can be rather complicated the way they fit together. But this is the notion of, this is an elementary notion of a foliation. Let me show you some other foliations. How about this? Right? How about just a stack? Z equals to, Z naught, whatever. This is a stack of horizontal planes is a foliation of the three-dimensional manifold R3. What differential equation does that correspond to? So over here, the the leaves in the foliation are solutions to a given differential equation, right? In fact, the leaves of the foliation are in the kernel. Well, that's not quite right. The tangent, right? If you look at these solutions, right, the tangent vectors like this, v, right? Oops, sorry. What can we say about those? V is an element of the kernel of, x dx plus y dy. The kernel of x dx plus y dy is a set of vectors, right? A set of vector fields, rather, which are sent to 0 under this differential form. And really, we want to restrict it. And we have the idea of restricting that to the, to the leaf. I guess that's also part of this. But so I guess my question is over here. What, if this, let's say that this is omega. So if you think about tangent vectors like these guys, V is an element of the kernel of what form? See, but V would be something like A partial x plus B partial y, right? So if you feed that to a generic one-form omega, what do you get? You get A plus B. Because dx hits x, dx and dy are dual to partial x and partial y. In fact, those are the dual bases at each point. And so, well, okay, so but this is for all A and B too. What's that? Oh yeah, sorry, you're right. Yeah. Thank you. Daniel's not buying it. All right. But this is true for all AB. It forces omega 1 and omega 2 to both be 0. Omega 3 is free. In other words, dV is the kernel of something like omega 3 times dz. So, okay, so it's so there's like three really big ideas that we're going to need to come to terms with here as we try to understand foliations. The one is, of course, the notion of a foliation, that you can take this space and divide it up into pieces, right? The other idea is that these leaves, right? They have certain vectors which are tangent to them, right? And really, you could think about vector fields which are tangent, right? Like, that's really what we should think about, is a set of vector fields which are the vectors in the vector field always appear as tangent vectors to the tangent plane of the leaves. Those kinds of vector fields which line up, which match up with the leaves, would be called integrable. Or they'd be called integrable. Well, you could call them tangent vector fields, right? A tangent vector field here is what the tangent vector fields here are just basically multiples of the theta hat, geometrically, right?
Does V have a specific direction? Like you draw through both of those specifically going?
Oh, this is just different V. This could be V1 and V2 if you like. I was using, they're both in the kernel. Well, I mean, I could also take a V3, which was in the other, I mean, I'm just doing them in the natural direction for me, but this would also be a tangent vector. That's still allowed.
It doesn't imply a specific direction.
No, not particularly, no. So, you know, how do we discuss these vector fields which line up with the leaves, right? These are, you might call these tangent vector fields. What condition on vector fields, and then you can ask questions like, given a set of vector fields, how do you judge whether or not these vector fields can appear as like tangents to some foliation, all right? And so it turns out that there's a connection, and then of course you can play the other game, which is to look at the, you can look at the vector fields in terms of being in the kernel or the annihilator, if you like, of, V is in the annihilator of this form, right? You can look at the vector fields as being in terms of being in the annihilators of differential forms. And it turns out there's this really beautiful interplay between foliations, these vector fields which appear as tangent to the leaves, and also the kernels, the annihilators of differential forms. You can either look at things in terms of the bracket. Remember we talked about bracket of vector fields ever? I don't remember if we did or not. Not too much if we have. But, sorry, I'll wrap it up here. But basically the bracket of vector fields is what? So here, x and y are derivations, right? They're derivatives on smooth functions. This looks like it would be second order, but it's not. Turns out the second order pieces cancel, and you're again left with a derivation, a first order differential operator. And so the bracket of two vector fields is this. And when the brackets are 0, or if they're nice, if they're again just a linear combination of x and y, you get this so-called involutivity condition. And involutive vector fields, it can appear as tangents to leaves in these foliations. And it turns out that there's an equivalent way of characterizing these in terms of kernels of differential forms in some sort of really natural way. In other words, the ideal, you end up looking at this ideal of differential forms, which is closed under wedge products of themselves and also the exterior derivative. And then all of this, a wonderful example of all this then is given in terms of the application to the differential, to differential equations. We build up this jet space, and I don't know, I'll start again next time on. Our time wasn't wasted here. I'm just trying to get us started thinking about it. So, thanks guys.